Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be exploring the extraordinary animals of the Ice Age and the vanished world they once called home. This was not just a colder version of the Earth we live in today. It was an entire ecosystem of ice and extreme weather that persisted for millennia. Animals evolved remarkable bodies that allowed them to survive these hostile environments, while others migrated across vast frozen habitats to find food and shelter. Some species became giants unlike anything alive today. Others developed strange adaptations that scientists are still piecing together from fossils and frozen remains. Their bones can reveal how they moved through the landscape. Even their teeth can preserve evidence of what they ate and where they traveled. The deeper we look, the more surprising this lost world becomes. Some animals survived long after others disappeared, and ancient humans witnessed part of that transformation firsthand. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is settle in. Let your shoulders relax, and notice your eyes grow heavy. And as the day begins to gently fade away, join me as we explore this remarkable Ice Age world together. Let's begin. Woolly mammoths survived brutal winters with two completely different layers of hair. A woolly mammoth carried an outer coat of long guard hairs but could hang almost to the ground. Beneath it was a dense layer of shorter wool that trapped warm air close to the skin. This was only part of a much larger cold weather system. Several inches of fat could lie beneath the skin, while a compact body reduced the amount of heat lost to the surrounding air. Even the tail was shortened compared with elephants from warmer climates. These adaptations mattered because mammoths endured long periods when temperatures remained far below freezing and strong winds swept across open ground. Their coat was not necessarily the rich brown often shown in reconstructions. Genetic evidence suggests that some individuals may have carried lighter hair. Preserved carcasses have allowed scientists to examine actual strands that survived for thousands of years. That means the famous shaggy appearance is not simply an artist's guess. We can still touch the physical material that once protected these animals as they moved through some of the coldest inhabited landscapes on Earth. Saber-toothed cats carried canine teeth longer than those of any living cat. The upper canines of Smilodon could extend well beyond the lower jaw and reach remarkable lengths. In the largest species, they approached the size of a large kitchen knife. Yet these teeth were not built like the thick conical canines of a modern lion. They were flattened from side to side and had finely serrated edges. That gave them extraordinary cutting ability, but it also meant they needed to be used carefully. Smilodon probably did not simply bite into any part of a struggling animal and hang on. A violent twist against bone could damage such specialized teeth. Instead, the cat appears to have relied on powerful control of its victim before delivering a highly directed bite into softer tissue. Young individuals offer another surprise. Their adult saber teeth developed while the milk canines were still present, so the skull temporarily carried two sets of prominent upper teeth. Fossils preserve this strange stage of growth. The result was one of the most extreme dental weapons ever evolved by a mammalian predator. Giant ground sloths grew as large as elephants and walked across ancient America. The largest ground sloths were nothing like the small tree dwellers alive today. Megatherium could reach several tons in weight and stretch more than 6 meters from head to tail. Its body rested on enormous hind limbs and a heavy tail that could help form a stable tripod. This allowed the animal to rise and reach vegetation far above the ground. Fossil footprints show an equally unusual detail. Many ground sloths walked with the outer edges of their feet taking much of the weight because their huge claws curved inward. The result was a gait unlike that of almost any large mammal living now. These animals spread through South America and later expanded into North America after the continents became connected. Different species occupied forests, grasslands, deserts, and other environments. Some were modest in size, while others became among the largest land mammals in the Western Hemisphere. Their entire branch of giant terrestrial sloths eventually vanished. Only their much smaller tree-living relatives survived into the modern world. Dire wolves were not simply oversized versions of the grey wolves alive today. For generations, dire wolves were reconstructed as heavier cousins of familiar wolves. Ancient DNA changed that picture dramatically. Genetic studies show that their lineage separated from the ancestors of modern wolves millions of years ago. They were so distinct that researchers placed them in a different genus called Inosian. Their resemblance to grey wolves appears to have developed because both animals evolved as large, dog-like hunters, not because they were especially close relatives. Dire wolves had broader heads and more robust teeth than many living wolves. Their bodies were also strongly built for tackling substantial prey. They ranged widely through the Americas and survived until near the end of the last ice age. Curiously, genetic evidence has not revealed clear signs that dire wolves interbred with grey wolves or coyotes. That stands out because living members of the dog family often exchange genes when their ranges overlap. The dire wolf therefore represents an entire ancient branch of the canine family tree that disappeared without leaving a direct living descendant. Giant, short-faced bears ranked among the largest mammalian predators of the Ice Age. Arctodus simus was built on a scale that makes even a large modern grizzly seem less imposing. Exceptional individuals may have weighed close to a ton, although estimates vary considerably. Its limbs were unusually long, giving the animal a high-shouldered appearance and allowing it to stand remarkably tall. The shortened face that inspired its common name was partly an illusion created by the proportions of its skull. From nose to back, the head was still enormous. For years, this bear was imagined as a relentless high-speed hunter that chased down prey across open country. Modern biomechanical studies have complicated that picture. Its heavy build was not ideal for prolonged pursuit, and chemical evidence from bones suggests that its diet varied by region. It probably combined predation with scavenging whenever opportunities appeared. Such flexibility would have been useful across the immense territory it occupied. Fossils have been found from Alaska to Mexico. Few mammals could have challenged a full-grown individual directly, making it one of the most physically formidable animals in Pleistocene North America. Humans once shared entire landscapes with mammoths, cave lions, and woolly rhinoceroses. This overlap was not a brief meeting at the edge of prehistory. In Eurasia, generations of people lived among animals that now seem almost mythical. Neanderthals encountered many of them, and later, Homo sapiens entered the same environments. Archaeological sites contain butchered bones, tools, fireplaces, and other evidence showing that humans interacted directly with large Ice Age mammals. Some encounters ended in hunting. Others involved scavenging carcasses or collecting bone and ivory after an animal had died. People also carried these species into culture. Cave walls and portable objects preserve unmistakable images created by artists who had watched living animals move. Those depictions sometimes capture features that skeletons cannot show, including body outlines and external appearance. The relationship was therefore more complex than predator against prey. Large mammals provided food, raw materials, danger, competition, and subjects worthy of careful observation. For a substantial part of human prehistory, encountering a creature that is extinct today could have been an ordinary part of traveling through the landscape. Some Ice Age elephants survived on remote islands thousands of years after the mainland giants vanished. Isolation gave certain elephant populations an extraordinary second chapter. When rising seas separated islands from nearby continents, some mammoths became trapped in places with limited food and restricted space. Over many generations, natural selection favored smaller bodies that required fewer resources. On Wrangel Island in the Arctic Ocean, woolly mammoths survived until roughly 4,000 years ago. By then, the Great Pyramids of Egypt had already been built. Another remarkable population persisted on St. Paul Island in Alaska until several thousand years earlier. These late survivors were not hidden remnants of an unchanged Ice Age world. They lived on shrinking refuges while their mainland relatives had already disappeared. Their final populations were small enough that genetic problems became increasingly important. On Wrangel Island, ancient DNA reveals harmful mutations accumulating within the isolated herd. Environmental change also placed severe pressure on limited freshwater and vegetation. These island mammoths show that extinction did not happen everywhere at once. For some animals, geography postponed the final disappearance by thousands of years. American lions were considerably larger than most lions living anywhere in the world today. Panthera atrox roamed North America with a body built on an extraordinary scale. Fossil measurements suggest that large males may have exceeded the size of typical modern African lions by a substantial margin. The species stood tall on long limbs and carried a massive skull. Yet its exact place within the big cat family has been debated for decades. It was once treated as a kind of gigantic lion closely connected to populations in Eurasia. Genetic evidence supports a close relationship with the broader lion lineage, although its evolutionary history remains the subject of continuing study. These cats occupied a huge geographical range from parts of Canada into Mexico. Their fossils occur beside remains of horses, bison, camels, and other large mammals that could have provided prey. Some specimens have also been recovered from natural asphalt deposits, where predators were drawn toward trapped animals. The American lion vanished near the close of the Pleistocene. Nothing comparably large now occupies the same feline predator role across the continent. The Ice Age supported vast grasslands packed with enormous herds of grazing mammals. Much of the northern world was not buried beneath continuous ice. Beyond the glaciers stretched a cold and remarkably productive environment, often called the Mammoth Steppe. Grasses and other low plants dominated enormous areas from Western Europe across Siberia and into North America. The climate was dry enough to limit extensive forests in many regions, which created open feeding grounds for large herbivores. Reindeer, horses, bison, and other grazers could gather in impressive numbers. Their feeding also helped to maintain the landscape by removing vegetation that might otherwise change its structure. Nutrients returned to the soil through dung and decomposing bodies, creating a powerful ecological cycle. The productivity of these plains supported substantial predator populations as well. What makes this ecosystem especially fascinating is that nothing identical exists today. After the climate warmed, wetter conditions transformed much of the old steppe into forest, tundra, or bog. The famous animals did not simply disappear from a modern landscape. The landscape that had sustained many of them disappeared too. Many famous Ice Age giants disappeared within a remarkably short period of geological time. Near the end of the Pleistocene, large animals vanished from many parts of the world at rates that still provoke scientific debate. North America lost mammoths, mastodons, giant sloths, native horses, and several other major groups within a relatively narrow span. South America experienced an equally dramatic transformation. The timing differed between regions, which is one reason no single explanation fits every extinction perfectly. Rapid climate change altered rainfall, vegetation, and seasonal conditions as the planet emerged from the last glacial period. At roughly the same broad time, human populations were spreading into new environments and hunting large animals. Researchers continue to investigate how these pressures interacted. Some species may have been especially vulnerable because they reproduced slowly. Others depended on habitats that were shrinking quickly. The losses were so extensive that entire ecological relationships vanished with them. Predators lost prey, plants lost major consumers, and nutrient cycles changed. What survives today is only a reduced sample of the giant mammal communities that existed surprisingly recently in Earth's history. Woolly mammoths carried surprisingly small ears that helped conserve precious body heat. Modern African elephants have enormous ears filled with blood vessels. When warm blood passes close to the ear surface, heat can escape into the surrounding air. For an animal living through Arctic winters, that useful cooling system would become a serious disadvantage. Woolly mammoths evolved in the opposite direction. Their ears were dramatically smaller and more rounded, which reduced exposed surface area and helped prevent unnecessary heat loss. Frozen specimens have confirmed this anatomy directly, rather than leaving scientists to infer it from bones. One remarkably preserved mammoth calf from Siberia retained ears only a fraction of the size expected on a comparably sized warm-climate elephant. Small extremities also reduced the danger of frost damage. The same general principle can be seen in many cold-adapted mammals today, where ears and other projecting body parts tend to become more compact. This detail shows how completely mammoths were shaped by their environment. Even a feature as familiar as an elephant's ear was transformed when survival depended on keeping every possible degree of warmth. A mammoth's enormous tusks could preserve a record of its entire life. Tusks grew continuously from specialized upper incisors, adding new layers of dentine throughout the animal's life. Those layers can be studied almost like a biological archive. Researchers cut or scan tusks to identify growth patterns that reflect age and physical condition. The chemistry locked inside them can reveal something even more astonishing. Different landscapes contain distinctive combinations of chemical isotopes. Plants absorb those signatures, mammoths eat the plants, and the information becomes incorporated into growing tusk tissue. By sampling along the length of a tusk, scientists can reconstruct where an individual traveled at different stages of life. One celebrated study followed the movements of an Alaskan mammoth across tens of thousands of kilometers. Its tusk showed that the animal changed its range as it matured before eventually dying in northern Alaska. This transforms an apparently solid piece of ivory into a timeline. A tusk can preserve years of migration, diet, stress, and growth, allowing researchers to retrace journeys taken by an individual animal many thousands of years after its death. Mammoth calves may have stayed close to their mothers for many years. Mammoths belong to the elephant family, so scientists can use living elephants as one guide when interpreting their social lives. The fossil record adds more direct clues. Trackways sometimes preserve groups of different-sized individuals moving together, which suggests herds containing adults and youngsters. Young mammoths would have faced a long apprenticeship. They needed to learn where seasonal food could be found, how to negotiate difficult terrain, and how to respond to threats. A prolonged childhood would have allowed information to pass between generations. Female elephants today form stable family units where older individuals play important roles in decision-making, and mammoths may have followed a broadly similar pattern. Calves also depended on milk for an extended period, while gradually learning to process tougher vegetation. Fossil teeth can reveal changes associated with weaning and development. This matters because a mammoth herd was probably not just a temporary gathering of animals. It may have been a network of related individuals carrying ecological knowledge that helped younger members survive in a demanding and constantly changing environment. Some frozen mammoths still preserve hair, skin, muscles, and stomach contents. Permafrost can turn an animal death into an extraordinary time capsule. In parts of Siberia and Alaska, mammoths were sometimes buried quickly in frozen ground, where low temperatures slowed the normal processes of decay. The resulting remains can be far more complete than an ordinary fossil skeleton. Scientists have recovered carcasses with recognizable skin, internal organs, muscle tissue, and thick patches of hair. In exceptional cases, the digestive system still contains fragments of the animal's final meals. Those remains allow researchers to identify plants that were growing nearby shortly before death. One famous juvenile mammoth retained so much soft tissue that her body still showed delicate external features rarely preserved in fossils. Such specimens also contain ancient proteins and genetic material that can be studied with modern laboratory techniques. They are not perfectly preserved animals waiting to wake again. Chemical damage continues even in deep cold. Yet they provide something almost unparalleled in paleontology. Researchers can examine the actual biological tissues of a creature that died during the Ice Age. Mammoths repeatedly crossed between Asia and North America through ancient Beringia. During colder periods, so much ocean water became locked inside continental ice sheets that global sea level fell dramatically. The shallow floor of the Bering Strait emerged as dry land, connecting Siberia with Alaska across a broad region known as Beringia. Mammoths used disconnection more than once. Genetic evidence shows that populations moved between the continents during different stages of their evolutionary history. Beringia was not simply a narrow bridge exposed between walls of ice. At times it formed a vast inhabited landscape with vegetation capable of supporting large mammals. Animals could spread across it generation by generation without ever knowing they had crossed from one modern continent to another. The connection also worked as a filter because climate and habitat determined which species could successfully pass through. When sea levels later rose, the route disappeared beneath the ocean. Mammoth history on both sides of the Pacific therefore depended on a landscape that repeatedly appeared and vanished as Earth's climate shifted between colder and warmer phases. Columbian mammoths towered over their woolly relatives across warmer parts of North America. Not every mammoth was built for the Arctic. The Columbian mammoth inhabited much of temperate North America and could become considerably larger than the woolly species of the far north. Mature individuals often stood around 4 meters at the shoulder, with exceptionally large animals reaching even greater dimensions. Their environment demanded a different body design. They lacked the extreme cold adaptations associated with woolly mammoths, and reconstructions generally give them much less body hair. Their huge tusks could curve outward before sweeping inward, creating one of the most imposing profiles of any Ice Age herbivore. Columbian mammoths ranged through grasslands and open woodland across much of what is now the United States and Mexico. Fossil sites occasionally preserve groups of individuals, including spectacular concentrations in places where natural conditions trapped or killed repeated generations. Their enormous size also reminds us how misleading the phrase woolly mammoth can be when discussing mammoths as a whole. North America supported several forms, and some lived in climates that were relatively mild. Woolly and Columbian mammoths sometimes interbred where their ranges met. Species boundaries can look much cleaner in textbooks than they were in real Ice Age landscapes. Genetic material recovered from mammoth remains has shown that woolly and Columbian populations exchanged genes. Their ranges overlapped in parts of North America, creating opportunities for animals from different ecological backgrounds to reproduce. This discovery changed how researchers interpret the Columbian mammoth itself. Genetic studies suggest that its ancestry included contributions from lineages related to woolly mammoths and another much older mammoth population. Later contact added further genetic mixing. The result was an evolutionary history more tangled than a simple branching tree. Such interbreeding should not be surprising within the elephant family. Living elephant species can also produce hybrids under certain circumstances. For paleontologists, however, ancient DNA made the connection visible thousands of years after the animals disappeared. Bones that look different in size and shape can still contain evidence of shared ancestry. Ice Age mammoths were therefore not isolated categories. Their populations met, mixed, separated, and changed as climate repeatedly shifted the boundaries of their habitats. Mastodons preferred wooded habitats and browsed very differently from grass-eating mammoths. A mastodon may resemble a mammoth at first glance, but its teeth reveal a completely different way of feeding. Mammoth molars contained rows of enamel plates that formed broad, grinding surfaces. Mastodon teeth carried prominent rounded cusps that were better suited to crushing leaves, twigs, bark, and other coarse plant material. Fossilized stomach contents and microscopic wear support the picture of an animal strongly associated with browsing. Mastodons often occupied forests, wetlands, and wooded edges where shrubs and trees provided abundant food. Their bodies were also somewhat different from those of mammoths. They tended to be more heavily built, with a lower profile and a distinctive skull shape. The mastodon lineage had separated from the ancestors of modern elephants far earlier than mammoths had. This means two huge elephant-like animals could inhabit the same broad continent, while representing very different evolutionary histories and feeding strategies. To an Ice Age observer, they were not interchangeable giants. Each was adapted to a particular way of finding food in a changing North American landscape. Mammoth molars worked like enormous washboards for grinding tough vegetation. A mammoth's back teeth were among the most specialized tools in its body. Each molar contained numerous ridges of enamel held together by softer dental tissues. As the tooth wore down, those alternating materials created a rough, grinding surface capable of shredding abrasive grasses. This was essential because grass carries microscopic particles of silica that can wear teeth relentlessly. Mammoths solved another problem in an unusual way. Instead of keeping one permanent set of adult molars, they replaced their giant grinding teeth several times during life. New teeth developed at the back of the jaw and slowly moved forward as older ones wore away. Eventually, the exhausted tooth was pushed out and replaced. Only a limited number of these replacements were available. In very old animals, the final molars could become so worn that feeding became increasingly difficult. Paleontologists can use tooth position and wear to estimate an individual's age. A mammoth jaw therefore records not only diet, but also a slow mechanical countdown that accompanied the animal throughout its life. Ancient mammoth dung still reveals exactly which plants these giants were eating. In dry caves and frozen ground, even something as ordinary as dung can survive for thousands of years. These preserved remains are known as coprolites, and they can offer a surprisingly detailed look at an extinct animal's diet. Plant fragments may remain visible under a microscope, while pollen and chemical traces provide additional clues. Researchers can sometimes recover DNA from the plants that pass through the digestive system. That evidence reveals what was actually eaten rather than merely showing which plants happened to grow nearby. Mammoth diets varied with geography and season. Grasses were important in many populations, but herbs and other vegetation could also contribute substantially. This has helped overturn older images of the mammoth steppe as a monotonous world dominated by grass alone. The vegetation was often richer and more diverse than that. Dung also preserves information about parasites and microorganisms associated with the digestive tract. A single preserved dropping can therefore become a miniature ecological record. It captures one animal's meal while also preserving traces of the wider biological community surrounding it. Smilodon had extraordinarily powerful forelimbs for restraining large and struggling prey. Its front legs were thick with muscle and supported by unusually robust bones. This gave the cat tremendous strength at close range. Rather than depending on a long pursuit, Smilodon seems to have been built for a sudden attack that ended with physical control. Once it reached a large herbivore, those forelimbs could help pull the victim off balance and keep dangerous movement under control. That ability mattered because its specialized teeth were most effective when the target could no longer twist violently. The shoulders were also heavily developed, which gave the animal additional power when wrestling with prey. This combination created a predator unlike the modern cheetah or wolf. Speed over distance was not its greatest advantage. Smilodon relied on explosive force during the critical seconds after contact. Fossil skeletons revealed just how extreme this specialization became. The bones of the front body looked disproportionately strong compared with those of many living cats. It was an animal shaped for one of the most dangerous moments in predation, physically overpowering another large mammal at exceptionally close range. Saber-toothed cats could open their jaws far wider than modern big cats. A living lion can open its mouth impressively wide, but Smilodon pushed feline anatomy to another level. Reconstructions of the skull suggest a maximum gape approaching 120 degrees. That enormous opening created room for the elongated upper canines to clear the lower jaw and reach deeply into a target. Achieving it required changes throughout the skull and jaw muscles. The lower jaw could rotate farther downward than in modern cats, while the arrangement of muscles allowed useful biting force even near the limits of that movement. The result looked almost impossible when the mouth was fully opened. Those adaptations were not simply for display. Without such flexibility, the famous teeth would have been awkward weapons because their length could restrict how the cat positioned its jaws. Smilodon therefore evolved an entire feeding mechanism around them. Its skull was not merely a normal cat skull, carrying oversized teeth. Many parts worked together to accommodate one highly unusual hunting system. The spectacular gape was one piece of engineering that made the saber-toothed design possible. Smilodon's famous canine teeth were formidable but surprisingly vulnerable to sideways forces. Length gave these teeth extraordinary reach, yet it came with a mechanical cost. A long blade is easier to bend than a short, thick spike, and the same principle applied to Smilodon's upper canines. Their flattened shape made them effective at penetrating and cutting soft tissue, but strong sideways twisting could place dangerous stress on them. Computer models and studies of fossil teeth support the idea that Smilodon needed to position its bite carefully. A struggling animal could potentially damage a canine if the tooth struck bone at the wrong angle. Broken specimens are known, proving that accidents did happen. This vulnerability helps explain why the rest of the body became so important during an attack. Restraining prey first would reduce violent movement before the teeth were driven in. It also challenges the popular image of saber-toothed cats simply biting through anything in their path. Their weapons were specialized instruments rather than indestructible daggers. Evolution had created a remarkable trade-off. Smilodon gained a devastating cutting system, but success depended on using it with control rather than brute force alone. Thousands of saber-toothed cat fossils have emerged from California's La Brea tar pits. The famous deposits in Los Angeles preserve one of the richest records of Ice Age predators anywhere on Earth. Natural asphalt seeped to the surface there for thousands of years. Water and dust sometimes covered the sticky material, making it difficult for animals to recognize the danger. A trapped herbivore could attract carnivores and scavengers from considerable distances. Those newcomers might then become trapped themselves. This predator-trap effect helps explain why Smilodon remains occur in such extraordinary numbers at La Brea. Researchers have recovered bones from well over 1,000 individuals. The collection includes adults of different ages and animals carrying evidence of injuries or disease. Because so many specimens come from one area, scientists can study variation across a population rather than relying on a handful of isolated skeletons. They can examine growth patterns, damage, anatomy, and even signs of repeated physical stress. La Brea therefore provides far more than dramatic fossils. It offers something close to a population-level archive of one of the most iconic predators of the Pleistocene. Injured Smilodon sometimes survived long enough for serious broken bones to heal. A major fracture can be devastating for a predator that depends on strength to capture food. Yet fossils from saber-toothed cats sometimes show severe injuries that had clearly begun to repair before the animal died. Broken limbs fused back together. Damaged joints developed extensive new bone. Some individuals survived conditions that must have reduced their hunting ability for weeks or longer. This raises an intriguing question about how they continued to eat. One possibility is that Smilodon could scavenge while recovering. Another is that social companions may sometimes have tolerated injured individuals around shared food. That idea remains debated because fossils cannot directly reveal social behavior. Even so, prolonged survival with debilitating injuries is difficult to ignore. One famous specimen had severe hip damage yet lived long enough for the surrounding bone to remodel extensively. Whatever kept such animals alive, they were not always lost immediately after serious injury. These fossils capture something unusually personal. Instead of sharing only how Smilodon killed, they reveal individuals enduring pain and continuing to survive despite bodies that no longer worked perfectly. Scimitar-toothed cats had shorter canines and longer legs than their famous saber-toothed relatives. Homotherium belonged to the saber-toothed cat family, but it followed a very different design from Smilodon. Its upper canines were flattened and serrated, yet noticeably shorter. The body was also more lightly proportioned, with comparatively long front limbs and a sloping back. This gave the animal a profile, sometimes compared with that of a hyena. Its anatomy suggests greater ability to travel efficiently across open ground. Rather than specializing entirely in explosive grappling, Homotherium may have pursued prey over longer distances before closing in. Fossils occur across enormous areas, which fits an animal capable of moving through varied open environments. Its teeth also show adaptations for slicing flesh with repeated bites. The name scimitar-toothed cat reflects the curved cutting shape of the canines. These predators demonstrate that saber teeth were not a single evolutionary experiment. Different cats modified the basic idea in different directions. One lineage emphasized immense stabbing canines and powerful forequarters. Another combined shorter blades with a body better suited to covering ground, producing a completely different approach to hunting large mammals. Homotherium survived across an enormous range spanning several continents. Few large Ice Age predators achieved such geographical reach. Fossils of Homotherium have been found across Africa, Europe, Asia, and the Americas at different stages of its history. That distribution placed related populations in environments separated by vast distances and dramatically different climates. The genus first appeared long before the final glacial period and persisted for millions of years. In some regions, it vanished relatively early. Elsewhere, it survived much later than scientists once realized. Discoveries from the North Sea showed that Homotherium remained in northwestern Europe surprisingly late in the Pleistocene. Ancient DNA has also helped reveal relationships between populations separated by continents. Such longevity suggests impressive ecological flexibility. Homotherium lived through repeated climate swings and major changes in available prey. Its success cannot be explained by one narrow habitat alone. The animal followed large herbivores across landscapes that repeatedly expanded and contracted as temperatures changed. Its fossils therefore trace more than the history of a predator. They reveal a lineage that managed to remain widespread through an extraordinary span of environmental upheaval before finally disappearing. Cave lions lived surprisingly far north within the cold landscapes of Ice Age Eurasia. Lions today are associated mainly with warm climates, which makes their Pleistocene distribution startling. Cave lions reach deep into northern Eurasia and inhabited regions that experienced severe winters. Their range extended through Europe and across Siberia. Evidence has even been found near the Arctic Circle. These animals were not living inside caves as their normal habitat. The name comes largely from fossil discoveries and ancient artwork found in caves. In life, they hunted across open landscapes where cold-adapted herbivores were abundant. Their bodies were large, which may have helped reduce heat loss while allowing them to tackle substantial prey. Frozen cubs discovered in Siberian permafrost have transformed what scientists can learn about them. These extraordinary specimens preserve fur and other soft tissues that ordinary skeletons cannot provide. Their existence so far north changes the familiar picture of the lion family. Lions were once creatures of icy steppes as well as warmer plains. The modern range represents only a small remnant of the environments this lineage occupied during the Pleistocene. Prehistoric artists depicted cave lions thousands of years before science formally described them. Long before paleontologists reconstructed cave lions from bones, people who actually encountered them recorded their appearance. Images from European caves show large cats with unmistakable feline bodies. Some lack the heavy mane associated with modern male African lions. Others include details such as rounded ears and tufted tails. These drawings matter because bones cannot preserve features like fur patterns or the amount of hair around the neck. Artists working tens of thousands of years ago therefore left evidence that modern science can compare with anatomy and genetics. One extraordinary group in Chauvet Cave shows several lions together in a hunting scene. Their bodies appear alert and purposeful rather than symbolic or fantastical. Whoever created those images had watched real animals closely enough to understand their proportions and movement. The paintings also remind us that cave lions were not remote fossils to the humans of the time. They were living predators occupying the same landscapes. Some of our best visual information about an extinct mammal was created by people who knew exactly what it looked like. The American lion ranged from cold northern regions deep into warmer North America. Its fossils reveal a predator capable of occupying an extraordinary span of environments. Remains have been found in areas that stretched from the northwestern parts of North America through the United States and well into Mexico. Across that range, climate and vegetation could differ greatly. Some populations lived near cold steppe environments, while others occupied much warmer landscapes. Such breadth suggests that the species was not tied to one narrow ecological setting. Large-bodied herbivores occurred throughout much of its territory, providing potential prey wherever suitable conditions existed. The wide range also created regional differences in competition. In some areas, American lions shared landscapes with Smilodon. Elsewhere, they encountered bears, wolves, and other formidable carnivores. Fossil discoveries show that this enormous cat was part of predator communities far richer than anything found across the continent today. Its disappearance therefore removed more than one spectacular species. An entire large cat roll vanished from North American ecosystems. The places where it once hunted are now occupied by animals and landscapes that provide little hint of the predator that formerly lived there. Dire wolves possessed a genetic lineage profoundly different from living grey wolves. For more than a century, their skeletons encouraged scientists to place dire wolves close to familiar wolves. The resemblance was convincing because both had long muzzles and bodies designed for terrestrial hunting. DNA eventually exposed a much deeper separation. Researchers recovered genetic material from fossils, and found that the dire wolf lineage had diverged from the ancestors of wolves and coyotes several million years earlier. That makes the similarity between them a striking example of evolution producing comparable forms in related but distinct lineages. The genetic discovery was especially surprising because morphology alone had pointed toward a much closer relationship. It also revealed how much information can remain hidden inside old bones after their external shape has been studied for generations. Dire wolves were not a heavier regional branch of the grey wolf story. They represented their own long, independent experiment in canine evolution. By the time humans entered many of their habitats, this lineage had already existed separately for an immense span of time. Its extinction erased a branch that had no exact counterpart among living dogs. Dire wolves survived for millions of years without leaving any known living descendants. Their lineage endured through repeated climatic upheavals and major changes in the animal communities of the Americas. Fossils related to dire wolves appear well before the final stages of the Ice Age, showing that they were not short-lived specialists that emerged just before extinction. Over time, they developed into heavily built predators suited to environments rich in large prey. Yet when the lineage disappeared near the end of the Pleistocene, it ended completely. No modern canine has been shown to descend directly from them. Grey wolves, coyotes, jackals, and domestic dogs belong to other branches. This makes the direwolf story unusually final. Many extinct animals survive indirectly through descendants that carry part of their evolutionary heritage. Dire wolves do not appear to have that continuation. Their genetics survive only in ancient material recovered from fossils. Every living dog on Earth therefore belongs to a family line that took a different path. The formidable predator, represented by thousands of fossil bones, became an evolutionary dead end, despite millions of years of previous success. La Brea has preserved dire wolves in astonishing numbers compared with many other predators. Dire wolf remains are among the most abundant large mammal fossils recovered from the asphalt deposits. Thousands of individuals are represented, giving scientists an unusually detailed sample of a vanished predator population. Their abundance probably reflects the way the traps worked. A struggling herbivore offered an irresistible opportunity to carnivores that could detect distress or scavenging prospects. If dire wolves approached in groups, several animals might become trapped during a single event. Over many thousands of years, those episodes accumulated into an extraordinary fossil record. The sheer number of bones allows researchers to study questions that are difficult with rarer species. They can compare males and females, examine injuries, track changes through time, and measure variation between individuals. Teeth also reveal repeated contact with hard material, which may reflect intensive use of carcasses. La Brea transforms the dire wolf from a creature known through isolated specimens into one of the best sampled extinct carnivores anywhere. Few prehistoric predators have left behind such an enormous collection of individual lives concentrated in one place. Ice Age grey wolves survived an extinction crisis that eliminated several competing carnivores. When the Pleistocene ended, grey wolves faced enormous ecological disruption. Large prey populations were changing rapidly, and several powerful carnivores disappeared from the same landscapes. Yet, wolves endured. Their survival may partly reflect behavioral flexibility. Grey wolves can hunt animals of very different sizes, scavenge when necessary, and live in a wide range of habitats. Pack behavior also allows them to adjust hunting strategies according to available prey. These traits could have provided options when ecosystems changed faster than more specialized predators could tolerate. Genetic evidence suggests that wolf populations themselves were not untouched. Ancient lineages vanished and were replaced or mixed with others as prey communities shifted. The animals that survived were therefore part of a changing population rather than a perfectly continuous one. their story provides an important counterpoint to extinction. The end of the Ice Age was not simply a dividing line between doomed giants and modern survivors. Some large predators managed to pass through the crisis by changing with it. Grey wolves emerged into the Holocene after surviving one of the greatest ecological reorganizations in recent mammalian history. Ancient wolf populations changed dramatically as the Ice Age megafauna around them disappeared. DNA and fossil evidence reveal that many Pleistocene wolves were not identical to the wolves occupying the same regions today. Some ancient populations possessed skulls and teeth associated with feeding heavily on large prey. As giant herbivores declined, these specialized wolf populations also disappeared. Later, wolves with different ancestry expanded into parts of their former ranges. This means the species survived while particular forms within it did not. The distinction is important because survival can hide profound evolutionary turnover. A person standing in Ice Age Eurasia might have encountered wolves whose genetic line eventually vanished, even though wolves as a whole remained successful. Changes in prey probably played a major role. When enormous herbivores became scarcer, predators adapted to exploiting them faced a transformed food supply. More flexible populations gained an advantage. Ancient genomes now allow researchers to follow these shifts with remarkable precision. The wolf's history therefore records the disappearance of megafauna indirectly. When the prey community changed, the genetic structure of one of its most adaptable hunters changed with it. Cave hyenas once hunted across Europe far beyond the range of hyenas today. Hyenas are now strongly associated with Africa and parts of Asia, but their Ice Age distribution reached deep into Europe. Cave hyenas occupied landscapes as far north as Britain during suitable climatic periods. They were closely related to the spotted hyena and were powerfully built. Their presence in cold environments can seem surprising, yet Pleistocene Europe often supported abundant large herbivores that provided substantial hunting and scavenging opportunities. These hyenas shared territory with formidable competitors, including wolves and large cats. Their crashing jaws gave them access to parts of carcasses that many other carnivores could not exploit as effectively. Fossil sites show that they fed on horses, rhinoceroses, deer, and other mammals. Climate eventually helped contract their range as European environments changed. Human competition may also have mattered in some places. Their disappearance from the continent leaves a misleading modern picture. Hyenas were once an important part of European predator communities. In regions that now seem completely outside their natural world, their calls would once have been part of the Ice Age night. Ice Age hyenas carried enormous bones deep inside caves to feed. Some caves contain such dense accumulations of gnawed bones that researchers can reconstruct repeated visits by generations of hyenas. Powerful jaws allowed these animals to drag large pieces of carcasses from kill sites or scavenging locations back toward sheltered dens. Once inside, they chewed bones intensively to reach nutritious marrow and grease. Their teeth left distinctive marks that can still be recognized by specialists. Coprolites found nearby provide additional evidence of prolonged occupation. Together, these remains can identify a cave as a carnivore den rather than simply a place where bones washed in naturally. The behavior created accidental archives of the surrounding ecosystem. Animals that may never have entered the cave alive ended up represented there because hyenas transported their remains. A single den might contain bones from numerous prey species collected across many seasons. Paleontologists can therefore use a hyena's feeding habits to reconstruct the wider community outside. What was once a messy accumulation of discarded meals has become one of the richest sources of information about local Ice Age wildlife. Cave hyena dens preserve remarkable snapshots of vanished predator and prey communities. A well-preserved den can function almost like an ecological census assembled by the hyenas themselves. Bones identify the herbivores available in the surrounding landscape. Tooth marks show which carcasses were heavily processed. Shed juvenile teeth can reveal that cubs were raised inside the cave. Coprolites provide information about digestion and diet. Other carnivore remains may indicate competition or occasional conflict. Because deposits can build up through long periods, different layers may record environmental changes as local animal populations shifted. Researchers must carefully separate material brought in by hyenas from bones deposited through other processes. Once that work is done, the cave can reveal patterns that would be difficult to detect from scattered fossils alone. Some dens contain remains of species that otherwise leave relatively few traces in the region. In that sense, the predator acted unintentionally as a collector. Its choice of prey and habit of carrying food home concentrated evidence for future scientists. Thousands of years later, a den can preserve the structure of an animal community that has completely vanished from the surrounding landscape. Dholes once ranged across much more of Eurasia than their surviving relatives do. The modern dhole survives mainly in parts of southern and eastern Asia, but fossils show that its relatives once occupied an enormous geographical range. During the Pleistocene, dholes reached Europe and lived in regions that are now far outside their distribution. They were social hunters with a body plan suited to pursuing medium and large prey. Their success across such broad territory suggests that they could tolerate varied environments when food and competition allowed. The European fossil record shows them living alongside wolves, hyenas, and large cats. That made carnivore communities far more crowded than those in the same regions today. As climates changed and prey populations shifted, dholes gradually disappeared from western portions of their range. Competition with other predators may also have contributed, although the exact causes remain uncertain. Their modern distribution can therefore create a false impression of where these animals belong. The dhole lineage was once part of the Ice Age fauna of places now separated from its surviving populations by thousands of kilometers. Arctic foxes expanded far south during colder Ice Age phases. Today, the Arctic fox is strongly associated with polar regions, but glacial climates pushed its suitable habitat much farther toward the south. Fossils have been discovered in parts of Europe that now have temperate conditions. When cold open environments expanded, animals adapted to tundra could follow them. The fox's compact body and thick winter coat made it particularly effective in these harsh landscapes. It could survive on small mammals and scavenged remains while enduring conditions that excluded many warmer climate species. As temperatures rose, the ecological map reversed. Forests spread into former tundra, and Arctic fox populations retreated toward higher latitudes or isolated mountain refuges. Genetic studies of ancient remains show that some southern Ice Age populations did not simply move north and become modern Arctic foxes. Certain lineages disappeared completely. Their history demonstrates how dramatically animal ranges can shift without the species itself becoming extinct. A place that supports deer and woodland today might once have held a distinctly Arctic community because the climatic boundary between those worlds had moved hundreds of kilometers southward. Giant, short-faced bears stood extraordinarily tall when they rose onto their hind legs. The sheer height of Arctodus has helped make it one of the most intimidating mammals of the Pleistocene. Large individuals already stood high at the shoulder because of their elongated limbs. When one reared upright, its head could rise well above that of a standing person. Estimates differ depending on the specimen, but the largest bears may have approached 3.5 meters in total upright height. Bears do not normally walk long distances on two legs, so this posture was not their standard method of movement. It would instead have been useful for surveying surroundings, reaching, displaying, or confronting another animal. The effect must have been extraordinary. A bear already weighing several hundred kilograms could suddenly more than double its visible height. Its long limbs contributed strongly to that impression. Despite the common image of a monstrous predator towering over everything around it, size alone does not reveal its behavior. The same anatomy that made Arctodus visually overwhelming also belonged to an animal whose feeding strategy probably shifted according to local opportunities and conditions. The enormous Arctodus ranged from Alaska all the way into Mexico. This huge bear occupied one of the broadest north to south ranges of any famous Pleistocene carnivore in North America. Fossils occur in Alaska and Canada, across much of the continental United States, and into Mexico. That span exposed populations to very different temperatures and habitats. Northern animals lived in regions shaped strongly by glacial climates, while southern populations encountered much warmer environments. Such distribution argues against the idea that Arctodus depended on one highly specific ecosystem. Instead, it appears to have been capable of exploiting different food resources across a changing continent. Body size also varied geographically, with some of the largest individuals known from northern areas. Its range overlapped with numerous other carnivores, but the exact set of competitors changed from place to place. Wherever it lived, Arctodus entered communities already containing substantial predators and scavengers. The fossils therefore reveal an animal remarkable not only for its dimensions but for its adaptability. Few modern North American mammals occupy a comparable climatic span while maintaining such an imposing body size. South America produced an even heavier short-faced bear called Arctotherium angostidens. One specimen from Argentina shocked researchers with the scale of its bones. Estimates suggest that this animal may have weighed well above 1,000 kilograms, making it a contender for the largest known bear. It belonged to a South American branch of short-faced bears that evolved after bears entered the continent from the north. Early members such as Arctotherium angostidens encountered ecosystems filled with unusual native herbivores and powerful predators. The tremendous size of the first populations may have provided an advantage when competing over carcasses. Later, South American short-faced bears became smaller, perhaps as ecological conditions and competition changed. That reversal is fascinating because evolution did not simply drive the lineage toward ever greater size. Its most gigantic form appeared comparatively early. The enormous Argentine specimen also shows why the Ice Age cannot be understood by focusing only on Eurasia and North America. South America developed its own spectacular communities. Among them walked a bear that may have outweighed every living bear species and even surpassed the celebrated Arctodus in sheer mass. Cave bears ate surprisingly plant-rich deets despite their intimidating size. Their skulls carried large teeth and immense jaw muscles, yet chemical evidence from many European cave bear bones points strongly toward plant consumption. Nitrogen isotope values often resemble those expected from herbivores rather than dedicated meat-eaters. Their broad molars were also well suited to grinding vegetation. This does not mean every cave bear ate exactly the same foods throughout its enormous range. Diet could vary by region and season, and bears are capable of considerable flexibility. Even so, many populations appear to have relied heavily on plants. The contrast between appearance and diet is striking. An adult cave bear could be larger than many modern brown bears, but much of its daily life may have involved searching for vegetation rather than chasing prey. This dependence could also have made certain populations vulnerable during colder periods when plant foods became scarce. Their intimidating skeletons once encouraged ideas of a highly carnivorous monster. Modern analysis has revealed a more complicated animal. The cave bear's enormous body was often supported by a diet that came largely from the landscape rather than from hunted flesh. Generations of cave bears repeatedly used the same caves across ancient Europe. Some European caves contain the remains of hundreds or even thousands of cave bears. These astonishing concentrations were not produced by one catastrophic event. Animals returned to suitable caves again and again across many generations. The shelters provided protected places for winter dormancy, and some bears died naturally while spending long periods inside. Over time, their skeletons accumulated on the cave floor. Cubs and young animals are represented alongside adults, showing that these sites were connected to multiple stages of life. Repeated use sometimes produced layers of bones so dense that early explorers struggled to understand what they were seeing. The pattern also means particular caves became valuable resources within the landscape. A deep, dry chamber suitable for a huge bear was not necessarily easy to replace. This attachment to caves may later have become important when humans increasingly used the same sheltered spaces. The fossil deposits preserve something close to a long-term address. One cave could remain part of cave bear life for thousands of years, as countless individuals entered the darkness and never knew that others had done the same before them. Brown bears survived the Ice Age, while several gigantic bear relatives disappeared. Their survival reflects the value of versatility. Brown bears can eat an exceptionally broad range of foods and occupy environments from forests to open northern country. They can alter their behavior when local resources change, and populations differ greatly in body size and feeding strategy. During the climatic upheavals at the end of the Pleistocene, that flexibility may have helped them persist, while more specialized bears vanished. Brown bears themselves experienced major changes in range and population structure. Glaciers separated groups, warming climates reopened territory, and different lineages expanded into newly available regions. They were not untouched survivors waiting for the modern world to arrive. Their history was dynamic and sometimes precarious. Yet the species endured a period that eliminated cave bears and short-faced bears. This contrast provides a useful lesson about Ice Age extinction. The largest or strongest animal was not automatically the one most likely to survive. Ecological flexibility could matter more than physical dominance. Brown bears entered the modern era partly because they were capable of changing what they ate and where they lived. Polar bears were already evolving during the shifting climates of the Pleistocene. Their origins are closely connected to brown bears, and genetic evidence shows a complicated history of separation followed by occasional interbreeding. The lineage that became specialized for Arctic life developed characteristics suited to hunting on sea ice. Changes in skull shape, metabolism, fur, and body composition eventually produced an animal profoundly different in lifestyle from most brown bears. Yet the two remained genetically close enough to reproduce when they met. Ancient genomes reveal that gene flow occurred at different times in their history. Climate fluctuations repeatedly expanded and contracted sea ice, changing where polar and brown bear populations could encounter one another. This makes polar bear evolution less like a clean split and more like a branching line that occasionally reconnected. Fossils of early polar bears are rare, so genetics has become especially important for tracing their past. The familiar white Arctic predator was therefore forged during a world of unstable glacial cycles. Its evolution depended on the repeated advance and retreat of the very frozen habitat that would come to define the species. Some ancient bears left claw marks that remain visible on cave walls today. These marks offer a startling connection to individual animals because they record movement rather than simply preserving a body. Cave bears and other large bears sometimes scratched rock surfaces while moving through underground chambers. In certain caves, parallel grooves remain high on walls where a standing bear could reach them. Some scratches may have resulted from climbing or maintaining balance. Others could have been produced deliberately through rubbing or clawing behavior. Their exact purpose is not always clear, but the animal that made them was physically present at that precise spot. Tracks and polished surfaces can appear nearby, adding further evidence of repeated movement through the cave. Unlike a fossil bone that may have been shifted after death, a wall scratch can preserve an action where it happened. A bear entered the darkness, raised a paw, and dragged its claws across the stone. Tens of thousands of years later, the grooves can still be traced by human hands. Few forms of evidence make the behavior of an extinct animal feel so immediate. Cave bear skulls were once mistaken for the remains of mythical dragons. Long before paleontology existed, enormous bones discovered inside European caves demanded an explanation. Cave bear skulls could look especially strange to people unfamiliar with comparative anatomy. Their broad foreheads, huge openings, and formidable teeth did not easily match familiar domestic animals. In regions rich with dragon legends, some remains were interpreted through the stories people already knew. One famous example comes from caves near the Austrian town of Mixnitz, where huge quantities of cave bear bones were later studied scientifically. Elsewhere, supposed dragon bones were displayed or even ground into medicines because they were thought to possess unusual powers. As anatomy developed into a formal science, researchers gradually recognized that many of these remains belonged to extinct mammals. The transition from dragon to bear captures an important moment in how humans learned to read the fossil record. The bones themselves never changed. What changed was the framework used to explain them. A creature from the Ice Age had survived in cultural memory for centuries without anyone realizing what kind of animal it actually was. Competition for caves may have brought humans and cave bears into direct conflict. A good cave offered protection from weather and could remain useful across generations. That made certain shelters valuable to both large bears and prehistoric people. Archaeological deposits sometimes show periods of bear occupation alternating with periods of human use. In other cases, remains occur close together. This does not prove that humans routinely fought cave bears for shelter, but it establishes clear potential for competition. A family entering a promising cave could discover that a massive animal already regarded it as a winter refuge. Bears returning to traditional sites might also encounter human occupants. Some cave bear bones show evidence of cutting or other human modification, which proves direct interaction at least occasionally. Researchers continue to debate how important hunting and competition were in the species' decline. Climate-driven changes in food were probably significant as well. Even without a simple explanation, the overlap is remarkable. The same underground chambers that preserve prehistoric art and human tools can also contain generations of bear remains, recording two powerful mammals repeatedly drawn toward the same scarce shelters. Megatherium was a ground sloth massive enough to rival an elephant in weight. At first glance, its skeleton hardly resembles the slow tree sloths we know today. Megatherium could weigh several tons and stretch around 6 meters from nose to tail. Its enormous pelvis anchored powerful hind limbs, while the tail was thick enough to help support the body. Despite this size, the animal was a plant eater rather than a giant predator. It probably moved through open woodland and grassland while feeding on vegetation that smaller animals could not reach. Its skull was relatively small compared with the rest of its body, which made the huge torso look even more extraordinary. Fossils were among the first giant extinct mammals to attract serious scientific attention in Europe after specimens arrived from South America during the 18th century. They helped establish a revolutionary idea. Entire species could disappear from Earth. Megatherium was therefore important, not only because of its size. Its bones helped change how humans understood extinction itself. A creature larger than almost any modern land mammal had once flourished, then vanished completely. Some giant ground sloths could rear upright and reach vegetation far overhead. Their hind limbs and enormous tails could work together as a stable three-point support. Once balanced this way, a large sloth could raise its front body and extend its forelimbs toward leaves well beyond the reach of most other herbivores. The claws then became useful for pulling branches closer rather than simply serving as weapons. This feeding posture allowed species such as Megatherium to exploit vegetation several meters above the ground without developing the long neck of a giraffe. Their skeletons preserve the clues. Massive pelvic bones carried the animal's weight, while thick tail vertebrae showed that the tail was capable of bearing considerable force. Fossil trackways suggest these animals normally traveled on four limbs, so standing tall was probably a temporary posture used during feeding or defense. The sight would have been extraordinary. An animal that already approached elephant scale could suddenly lift the front half of its body high above the surrounding vegetation. Ice Age South America had produced a browser that reached upward through sheer body mechanics rather than through a specialized neck. Ground sloths carried powerful claws that served purposes far beyond simple defense. The great curved claws on their forefeet are among the most dramatic parts of a ground sloth skeleton. They certainly could have made a dangerous predator think twice, but fighting was probably only one use. Different species depended on these claws for feeding and interacting with their surroundings. A sloth could hook branches and drag them closer to its mouth. Some may have used their forelimbs to tear at tough vegetation or disturb soil while searching for roots. Others probably dug shallow hollows or altered the ground around feeding sites. Certain cave walls even preserve scratches attributed to large sloths, showing how readily those claws marked solid surfaces. Because the claws curved so strongly, the animals could not simply place them flat against the ground while walking. Their feet evolved unusual postures that kept the tips protected. This created an entire style of movement around the presence of the claws. They were not oversized accessories attached to an otherwise ordinary herbivore. They shaped how the animal stood, walked, fed, and potentially defended itself throughout its life. Shasta ground sloth dung has survived for thousands of years inside dry caves. Few extinct mammals have left such personal evidence behind. In caves of the American Southwest, researchers have discovered large masses of dried dung produced by Nothrotheriops chastensis. The arid conditions prevented complete decay, preserving meals eaten more than 10,000 years ago. Inside these deposits are recognizable fragments of desert plants. Scientists have identified items such as yucca and agave, which reveal that the animal could survive on vegetation that seems surprisingly tough and uninviting. Because different layers accumulated over time, the dung can also show how diet changed as local environments shifted. Plant DNA and pollen add even more detail. These deposits transform a dry cave floor into a record of daily life. Bones tell us what the animal looked like, but dung reveals what it actually swallowed on particular journeys through the landscape. Some caves contain enough material to suggest repeated use over long periods. The humble remains of digestion have therefore become one of the clearest windows into the ecology of a vanished giant that once wandered deserts across western North America. Certain ground sloths wandered into harsh desert landscapes that look surprising today. The popular image of a giant sloth often places it among lush vegetation, but some species were remarkably comfortable in arid country. Shasta ground sloths occupied parts of what are now Nevada, Arizona, and the surrounding Southwest. Their remains occur in caves overlooking terrain that receives little rainfall today. These animals were smaller than elephant-sized Megatherium, which may have made it easier to survive where plant productivity was limited. They also appear to have eaten drought-tolerant vegetation that many grazers would find difficult to use. The landscape itself was not identical to the modern desert, because Ice Age climates supported different plant communities. Even so, conditions could still be dry and challenging. Ground sloths succeeded there without the speed of a horse or the water-saving reputation of a camel. Their survival depended on a completely different strategy built around selective feeding and slow energy use. Discovering their remains in these environments widens the picture of sloth evolution. These animals were not confined to forests. Their dynasty had adapted to some of the most demanding habitats in the Americas. Mylodon remains became so well preserved that early explorers thought they looked recent. In the late 19th century, discoveries from a cave in Patagonia created extraordinary excitement. Pieces of hide still carried coarse hair, while bones and dung lay preserved in the dry interior. The material belonged to Mylodon darwinii. This large ground sloth had vanished thousands of years earlier, yet some remains looked fresh enough to inspire speculation that the species might still survive somewhere in remote South America. Expeditions were even encouraged by the possibility of finding a living giant sloth. No surviving population was discovered, but the episode shows how striking the preservation was. The cave became famous as Cueva del Mylodon and remains one of Patagonia's iconic fossil sites. Its dry conditions protected tissues that normally disappear soon after death. Preserved skin reveals a remarkable layer of small, bony structures embedded within it, which may have added protection to the body. For early observers, the distinction between ancient and recent suddenly became difficult to judge. An extinct animal seemed, for a moment, as though it might still be hiding beyond the horizon. Ancient humans encountered giant ground sloths before these remarkable animals finally disappeared. The overlap is preserved at archaeological sites across the Americas. Stone tools occur in the same broad time period as the last ground sloths, and some bones carry marks consistent with human processing. One particularly important site in South America has produced sloth remains associated with evidence of human activity, although researchers continue debating aspects of individual discoveries. Footprints offer an even more immediate connection. At White Sands in New Mexico, trackways preserve humans and giant sloths moving across the same ancient surface. Some sloth tracks change direction near human prints, suggesting the animals may have reacted to nearby people. Whether every encounter involved hunting is impossible to know. Humans could have observed, avoided, scavenged, or pursued these enormous herbivores depending on the circumstances. What is certain is that ground sloths were not creatures from some impossibly remote age before humanity. People saw them alive. Stories may once have been told about animals whose entire terrestrial way of life has since vanished. The boundary between human history and their extinction is surprisingly thin. Tree sloths are the small surviving relatives of a once astonishingly diverse dynasty. Modern sloths represent only a tiny fragment of what their broader evolutionary group once became. During the Ice Age, relatives ranged from modest animals to giants weighing several tons. Some lived on the ground across open landscapes. Others climbed, dug, or occupied very different ecological roles. The group spread throughout South America and eventually reached North America after the continents became connected. Today's 6 living species all inhabit trees in tropical regions, which can make the entire lineage seem specialized for slow arboreal life. The fossil record tells a far bigger story. Their ancestors experimented with body sizes and lifestyles that have no direct modern equivalent. Even their metabolism and movement may have varied substantially across species. When most ground sloths disappeared near the end of the Pleistocene, only the tree-dwelling branches survived. Looking at a living sloth is therefore a little like seeing the final handful of leaves on an enormous evolutionary tree. Its small body does not represent what sloths once were. It represents the narrow portion of a remarkable radiation that happened to make it into the present. Some extinct sloths adapted to life in water millions of years before the Ice Age. Along the ancient coast of what is now Peru, a lineage called Thalassochnus gradually became increasingly aquatic. These animals lived well before the peak of the Ice Age, but their story reveals how experimental sloth evolution had already become. Early species probably fed near the shoreline. Later forms developed denser bones that helped counteract buoyancy, allowing them to remain submerged more easily while feeding. Their limbs and tails also changed, as generations spent increasing amounts of time in marine environments. They may have grazed on seagrasses or other coastal vegetation. This transformation took place step by step across millions of years, and fossils preserve several stages of the transition. It is an extraordinary contrast with modern sloths hanging from rainforest branches. Members of the same broad mammalian group once entered the Pacific and adapted their skeletons for underwater feeding. They disappeared long before the final Pleistocene extinctions, but their existence proves how misleading a modern snapshot can be. Sloths evolved forms that climbed trees, walked across plains, reached elephant size, and even ventured into the sea. Ground sloths helped disperse plant seeds across landscapes that no longer exist. Large herbivores do more than consume vegetation. They transport it. Seeds swallowed with fruit can survive passage through the digestive system and emerge far from the parent plant inside a package of natural fertilizer. Giant ground sloths were capable of moving much larger seeds than most surviving mammals in the Americas. This has led researchers to investigate whether certain plants evolved partly around relationships with now extinct megafauna. Some living fruits contain seeds that seem inconveniently large for the animals that eat them today. One possibility is that their original dispersers vanished at the end of the Pleistocene. Ground sloths are among the candidates. Their daily movements could have carried seeds across broad territories and helped plants colonize new patches of suitable habitat. When these herbivores disappeared, plants did not necessarily become extinct with them. Some gained replacement dispersers or survived through other methods. Yet their ecological system had changed. A modern forest may therefore contain living plants whose fruits still make more sense when imagined inside the mouth of an enormous extinct mammal. Diptodonts were enormous armadillo relatives enclosed inside rigid shells of fused bone. Imagine an armadillo enlarged until its body approaches the size of a small car, then replace its flexible bands with a solid armored dome. That was the basic design of many glyptodonts. Their protective covering was formed from bony plates within the skin. Unlike the movable armor of living armadillos, much of the glyptodont shell became fused into a rigid structure. This created extraordinary protection across the back and sides. Even the head carried a bony cap. Such defense was valuable in South America, where large saber-toothed cats and other predators shared the landscape. The trade-off was mobility. A heavily armored body could not twist with the flexibility of a modern armadillo. Glyptodonts therefore developed a distinctive compact shape supported by powerful limbs. Some species weighed well over a ton. Their fossils were so unusual that early scientists struggled to understand what kind of creature they represented. Eventually, anatomy revealed the connection to armadillos. One of the strangest giants of the Ice Age turned out to be an extreme member of a family that still survives today in much smaller form. Some glyptodont tails ended in heavy structures capable of delivering powerful blows. Armor protected the body, but certain glyptodonts added an active weapon at the rear. Their tails contained rings of bony armor and could terminate in an enlarged club-like structure. The most spectacular examples belong to forms such as Doedicurus. Muscles at the base of the tail would have allowed the animal to swing this heavy end from side to side. Researchers have studied the mechanics to estimate how much force such a blow could generate. The weapon may have served in defense against predators, but another possibility is especially intriguing. Diptodonts might have used their tails against members of their own species during competition. Damage found on some shells has been interpreted as possible evidence of impacts from tail weapons, although exactly how often this occurred remains debated. Either way, the animal was far from helpless beneath its armor. A predator approaching from behind faced both a hardened shell and a moving mass of bone. This made certain glyptodonts one of the closest mammalian equivalents to the armored, club-tailed dinosaurs that had vanished tens of millions of years earlier. Glyptodont armor was made from thousands of small bony plates called osteoderms. Each osteoderm grew within the skin and joined neighboring plates to create the great shell. Their surfaces often carried distinctive patterns of grooves and raised areas, which helped paleontologists identify different species. Some plates were only a few centimeters across, yet thousands together produced a structure capable of covering an animal weighing more than a ton. The shell was not an external object like a turtle's removable-looking shield. It was part of the skeleton and developed with the animal. Different regions of the body used armor in different ways. The head carried its own protected cap, while the tail could be surrounded by increasingly specialized rings. Fossil fragments are common because individual osteoderms can survive even after an entire skeleton has broken apart. For early collectors, these strange pieces sometimes appeared before complete animals were understood. Once assembled, they revealed an extraordinary construction method. Protection did not come from one gigantic bone. It came from countless smaller units integrated into a single defensive surface, creating one of the most elaborate armored systems ever evolved among mammals. Giant armadillo relatives shared South America with saber-toothed cats and enormous sloths. Pleistocene South America supported mammal communities unlike any ecosystem alive today. A glyptodont could feed near a ground sloth that weighed several tons, while Smilodon prowled the same region. These animals were products of a continent that had spent millions of years partly isolated from northern land masses. During that isolation, South American mammals evolved along distinctive paths. When the land connection through Panama formed, newcomers from North America arrived and mixed with the native fauna. Cats, bears, and other groups entered a world already occupied by strange herbivores. The result was a biological meeting on continental scale. Glyptodonts and giant sloths continued to thrive alongside these newer arrivals for millions of years. Their coexistence challenges the idea of the Ice Age as a single uniform mammoth world. South America had its own caste of giants and its own ecological history. Many belonged to lineages that evolved nowhere else. By the late Pleistocene, ancient southern forms and northern immigrants were living together in communities created by one of the greatest exchanges of land mammals in Earth's history. Doedicurus carried one of the most formidable tail clubs among Ice Age mammals. The end of its tail expanded into a massive bony sheath that would grow close to a meter long. Unlike a simple rounded club, this structure was flattened and sometimes equipped with areas that may have supported horn-like projections. The rest of the tail was protected by rings that allowed some movement while maintaining strength. Combined with the animal's huge armored body, this created a remarkable defensive system. Doedicurus itself could weigh around a ton or more, so the muscles moving the tail were anchored to a very substantial frame. Biomechanical studies suggest that swinging the weapon could generate enough force to cause serious injury. The exact target remains uncertain. Predators are an obvious possibility, but disputes between adult Doedicurus may also have encouraged the evolution of such extreme weaponry. The animal lived in South America until remarkably late in the Pleistocene. Humans therefore reached the continent, while these cub-tailed giants were still present. Few mammalian herbivores have ever combined body armor and a specialized striking weapon so dramatically. Pampathas looked like oversized armadillos, but lacked the fully rigid shells of glyptodonts. These extinct mammals belong to another armored branch of the same broad South American family. At a glance, they could resemble glyptodonts, but their bodies were built for greater flexibility. Instead of carrying one huge solid dome, Pampathas retained movable bands across part of the back. That made their armor more comparable to the arrangement seen in modern armadillos, although the animals themselves were much larger. Some reached around 2 meters in length and weighed well over 100 kilograms. Their teeth suggest a diet that may have included tough vegetation, which distinguished them ecologically from many living armadillos that rely heavily on insects. Pampathas spread beyond South America and reached parts of Central and North America. Fossils have been found as far north as the southern United States. Their existence reveals that armored mammals evolved several different solutions during the Ice Age. Glyptodonts committed to a rigid fortress-like shell. Pampathas retained more flexibility while increasing dramatically in size. Both strategies succeeded for millions of years before the lineages disappeared. Ancient humans may have used large glyptodont shells as convenient shelters. A complete glyptodont carapace could form a broad, curved structure large enough to cover part of a person. This has inspired the idea that people in South America might occasionally have reused abandoned shells as windbreaks or temporary shelters. Some archaeological interpretations have gone further and suggested purposeful use at campsites. The evidence remains limited, so it is safer to treat the idea as plausible rather than established behavior. Even so, the possibility makes sense when considering the object itself. A shell left after the animal died was already shaped like a low dome and made from thick bone. In open country with few large building materials, such a structure would have been difficult to ignore. Humans certainly encountered glyptodonts, and some sites preserve evidence that people processed their carcasses for meat. A shell, therefore, could have become useful after feeding was finished. Whether used for protection from weather or simply as a convenient barrier, the concept reveals how unfamiliar Ice Age landscapes were. Even the remains of an herbivore could provide something resembling ready-made architecture. Giant armadillo relatives spread north after the Americas became connected by land. For most of their evolutionary history, glyptodonts and their relatives were confined to South America. That changed after the Isthmus of Panama formed a continuous land connection between the continents. Animals began moving in both directions during what scientists call the Great American Biotic Interchange. Armored mammals were among the successful northbound travelers. Glyptodont relatives eventually reached Central America and parts of the southern United States. Pampathas traveled even farther into North America. Their expansion was not instantaneous. Populations moved gradually through suitable habitats over many generations. Along the way, they encountered predators and competitors that their ancestors had never faced. Some northern species developed local adaptations while retaining the unmistakable armor of their South American heritage. The journey demonstrates how a geological event can rewrite animal distribution. A rising strip of land changed migration routes across an entire hemisphere. Millions of years later, fossils in places such as Florida and Texas preserve evidence that creatures born from South American evolution eventually became members of North American Ice Age ecosystems. Glyptodonts belong to the same extraordinary mammalian branch as living armadillos. Their connection is deeper than superficial armor. Anatomical studies placed both groups within Xenothera. This is the distinctive South American mammal lineage that also includes sloths and anteaters. Molecular evidence from preserved proteins later strengthened the relationship between glyptodonts and armadillos. In fact, glyptodonts appear to sit within the broader armadillo family tree, rather than representing a completely separate armored experiment. That finding changes how their size is understood. A lineage containing small, burrowing animals also produced mammals weighing more than a ton and covered by rigid bone. Evolution had stretched the armadillo body plan almost beyond recognition. The relationship can still be seen in features of their vertebrae and armor, although a living armadillo gives little sense of just how extreme its extinct cousins became. When glyptodonts vanished, this enormous expression of the lineage disappeared with them. Modern armadillos are therefore survivors of a family that once occupied a much wider range of body sizes and ecological roles. Their modest appearance hides an evolutionary history that includes some of the strangest giants of the Pleistocene. South America's isolation helped produce Ice Age mammals found nowhere else on Earth. For tens of millions of years, South America functioned much like a gigantic evolutionary island. Its mammals diversified while separated from most northern land animals, producing lineages with no close modern equivalent elsewhere. Xenopterans became especially varied, and native hoofed mammals evolved body forms that sometimes resembled animals from completely different continents. Large predators included unusual marsupial relatives before northern carnivores eventually arrived. When the continental connection formed, this long isolation ended. New animals crossed south, while native groups moved north. Some old South American lineages survived the invasion and remained major parts of Ice Age ecosystems. Others declined over time. By the Pleistocene, the continent contained a remarkable mixture of ancient natives and newer immigrants. This history explains why its megafauna looks so different from the classic northern picture. Evolution had spent millions of years experimenting behind a geographical barrier. When humans eventually entered South America, they encountered the late survivors of that unique story. Many disappeared soon afterward, leaving modern ecosystems far less unusual than the ones that preceded them. North America was once home to native camels with remarkably long legs. During the Ice Age, camel relatives were familiar members of North American landscapes. One of the most striking was camelops, which stood taller than many modern camels and carried long limbs suited to traveling across open country. Fossils occur from the western United States into northern Mexico and farther north. The exact shape of its back remains uncertain because soft tissues do not fossilize easily, so scientists cannot simply assume it carried the same prominent hump seen in some living camels. Its skeleton tells a clearer story. Camelops was a substantial herbivore with a body adapted for covering ground efficiently. It fed on a mixture of available vegetation rather than being restricted to the desert plants associated with camels today. For early people in North America, such animals would have been part of the large herbivore community rather than exotic creatures from another continent. Their extinction near the end of the Pleistocene erased that association completely. Camels now seem foreign to North America, even though their family history there runs extraordinarily deep. Camels evolved in North America long before becoming symbols of African and Asian deserts. The camel family originated in North America more than 40 million years ago. Its earliest members were small and looked very different from the tall desert animals alive today. Over immense stretches of time, the group diversified into numerous forms. Some developed long necks and legs. Others remained relatively compact. Eventually, certain camel ancestors crossed from North America into Asia through Beringia. Those migrants gave rise to the Old World camel lineages that later became adapted to deserts and steppes. Another branch moved south into South America and eventually produced llamas, alpacas, guanacos, and vicuñas. The strange result is that North America served as the evolutionary birthplace for a family whose surviving members now live naturally elsewhere. Native North American camels disappeared near the close of the Pleistocene. When people today picture a camel beside desert dunes, they are seeing the endpoint of a journey that began on a completely different continent. Their famous adaptations were built upon an evolutionary history that started millions of years before camels ever reached the landscapes most strongly associated with them. Ice Age horses once thundered across North America before disappearing from the continent. Wild horses were abundant across much of North America during the Pleistocene. Fossils appear in enormous numbers, showing that they occupied grasslands and other open environments from northern regions to Mexico. Their evolutionary history on the continent stretched back tens of millions of years through ancestors with changing numbers of toes and increasingly specialized grazing teeth. By the Ice Age, recognizably horse-like forms were widespread. Then they vanished from North America around the end of the Pleistocene, along with many other large mammals. The reasons remain tied to the wider debate over climate change and human impacts. Yet horses did not disappear globally because populations had previously crossed into Eurasia. Their descendants survived there. This created one of the strangest geographical reversals in mammalian history. A lineage that had evolved for ages in North America disappeared from its birthplace while continuing elsewhere. For thousands of years afterward, the continent contained no horses at all. Archaeological sites and fossils are the only evidence that vast herds had once been part of its native ecosystems. Modern horses eventually returned to a continent where their ancestors had evolved. The return happened through human history rather than natural migration. Spanish expeditions brought domesticated horses to the Americas after European contact. Some animals escaped or were released, and their descendants spread rapidly through suitable environments. Indigenous peoples transformed horse culture across large parts of the continent, developing new ways of traveling, hunting, trading, and conducting warfare. Ecologically, the returning animals entered landscapes where members of their own family had been absent for thousands of years. This creates an unusual question about what counts as native. The domestic horses themselves descended from Eurasian populations shaped by human breeding. Yet the broader horse lineage had deep evolutionary roots in North America. Feral populations therefore represented both a return and something genuinely new. They were not identical to the Pleistocene species that had disappeared. Still, their feet touched ground where horse ancestors had been evolving for tens of millions of years. Few familiar domestic animals have such a dramatic story. The horse crossed continents, vanished from its birthplace, survived abroad, and eventually came back with humans. Steppe bison crossed Beringia and helped populate the Ice Age landscapes of America. Bison were not originally North American animals. Their ancestors evolved in Eurasia and eventually moved eastward through Siberia. During periods of low sea level, the Beringian landscape opened a route into Alaska. Steppe bison crossed that region and expanded into North America, where their descendants diversified. They became major herbivores across open habitats and played an important role in the ancestry of later American bison. Fossils and ancient DNA allow researchers to trace several waves of movement and population change. These were not small migrations involving a few wandering animals. Over time, entire populations spread into new territory as suitable grasslands opened ahead of them. Their arrival added another major grazer to ecosystems already filled with large mammals. They also became important prey for carnivores and eventually for humans. Modern American bison therefore carry the legacy of an Ice Age crossing that happened thousands of generations ago. The species now treated as an icon of North America belongs to a lineage that reached the continent through the same northern gateway used by many other Pleistocene travelers. Ancient steppe bison carried horns that spread much wider than those of many modern bison. Some Pleistocene bison possessed enormous horn cores that projected dramatically from either side of the skull. In bison priscus, these could create a span far broader than the compact horns of most living American bison. The horns were covered in keratin during life, which would have made their complete dimensions even greater than the surviving bone suggests. Such structures probably played important roles in competition and display. Large males could assess rivals before physical contact, while horn size may have communicated age or condition. The cost of growing and carrying them must have been substantial, which suggests they provided a meaningful reproductive advantage. Different bison lineages later evolved smaller horn arrangements as body form and ecology changed. Fossil skulls preserve this history beautifully because horn cores are durable and easily measured. A modern bison already looks formidable, but some of its Ice Age relatives would have presented an even wider silhouette. Their skulls show how dramatically sexual competition and environmental pressures could reshape one of the most recognizable herbivore designs on the northern plains. One famous frozen bison still preserves evidence of the predator that killed it. The specimen known as Blue Babe was discovered in Alaska during the 1970s and became one of the most remarkable Ice Age carcasses ever recovered. Its name comes from a blue mineral coating that formed on parts of the preserved skin. The animal was a steppe bison that died more than 30,000 years ago. Examination of the carcass revealed claw and tooth damage consistent with an attack by a large lion. The pattern suggests that the predator killed the bison and began feeding before the remains froze and became preserved. Scientists could therefore reconstruct part of an event that lasted only minutes but survived for tens of millennia. Blue Babe retained skin, muscle, and other tissues that rarely fossilize. Researchers even prepared a small portion of preserved meat during a publicized dinner, though such treatment would be unusual by modern standards. More importantly, the carcass captured direct evidence of predator and prey interaction. It is not merely a frozen body. It preserves the final violent encounter of one individual animal. Giant long-horned bison carried horn cores spanning an extraordinary distance across the skull. Bison latifrons developed some of the most spectacular horns known from any member of the cattle family. In the largest skulls, the distance between the outer tips of the horn cores could exceed 2 meters. The living keratin sheaths would have extended the full span even farther. These animals were also larger than modern bison and inhabited North America during earlier parts of the Pleistocene. Their immense horns may have functioned primarily in competition between males, rather than as specialized defenses against predators. Carrying such wide structures would have affected how the animal moved through dense vegetation, which may help explain its association with more open environments. Later, bison lineages reduced horn size substantially. That change could reflect shifts in habitat, social behavior, or the energetic cost of producing such extravagant structures. A complete bison latifrone skull gives an immediate sense of how different Ice Age bovids could be. The basic bison body was familiar, but evolution had stretched the headgear to proportions that no surviving North American herd can match. Musk oxen survived the Ice Age while many larger neighbors around them vanished. Their survival did not depend on escaping the cold. Musk oxen are built to endure it. Beneath their long outer hair lies kivute, an exceptionally fine, insulating underwool that protects the body through severe Arctic winters. During the Pleistocene, muskox relatives occupied a broader range than living populations do today. As climates warmed, their distribution contracted toward the far north. They survived by remaining associated with environments where their cold weather adaptations still worked. This makes them living representatives of mammal communities that once extended much farther south. Their social behavior also provides powerful protection. When threatened, adults can form defensive groups around vulnerable calves and confront predators with their horns. Modern populations have faced local disappearances and later reintroductions, so their survival history has not been effortless. Yet the lineage made it through the end Pleistocene upheaval that removed many other large herbivores. Seeing a muskox today means looking at an animal whose body still carries solutions shaped by Ice Age conditions. Its thick coat belongs to a world that has largely retreated toward the poles. Reindeer prospered across enormous stretches of the cold mammoth steppe. Few large mammals were as well suited to the shifting northern landscapes of the late Pleistocene. Reindeer ranged across broad parts of Eurasia and North America as open, cold habitats expanded. Their ability to travel long distances allowed herds to follow seasonal food across immense territories. Broad hooves helped them move over snow and soft ground, while a dense coat protected them in severe weather. Their diet included lichens during difficult seasons, which opened a food source unavailable to many competing herbivores. Reindeer also developed one of the most unusual antler systems among deer. Females commonly grow antlers as well as males, which can help them compete for access to feeding sites in winter. For prehistoric humans, reindeer became an enormously important resource in many regions. Bones at archaeological sites show repeated hunting and processing. Their hides, meat, antlers, and bones could all be useful. Unlike many iconic Ice Age herbivores, reindeer survived into the present. Their migrations still provide a living glimpse of the vast moving herds that once crossed much larger stretches of the northern world. Sager antelope once roamed far beyond the limited regions where they survive today. During the Ice Age, sager were not restricted to the great steppes of Central Asia. Fossils show that they ranged across enormous parts of Eurasia and even reached North America through Beringia. Their strange, swollen noses belonged to an animal that could thrive in dry, cold, open country. As glaciers advanced and grasslands expanded, suitable habitats stretched across regions where sager no longer live. Later, warming changed that map. Forests spread into former steppe, and populations retreated toward the remaining open landscapes of the east. The modern distribution therefore represents only a fraction of their former world. This matters because sager are often imagined as highly specialized animals tied to one remote region. In reality, their lineage once crossed a vast sweep of the northern hemisphere. Fossils from Western Europe show just how far that expansion reached. The species survived when many larger Ice Age mammals vanished, but its geographical empire collapsed. A living sager today is therefore not merely a curious modern antelope. It is a surviving fragment of an animal community that once stretched across continents. The sager's remarkable nose helps warm and filter freezing air before it reaches the lungs. That oversized downward-pointing nose is not an evolutionary accident. Inside it lies a complex system of passages lined with moist tissue and blood vessels. During bitter winters, incoming air is warmed before it travels deeper into the respiratory system. The same structure can also help trap dust during dry summer migrations across open steppe. This double function makes the nose useful in opposite seasonal extremes. Ice Age environments repeatedly exposed sager to both cold and dusty conditions, so an adaptable respiratory system offered a real advantage. The nose may look exaggerated to human eyes, but it is a finely tuned piece of survival equipment. Male sager also use nasal anatomy during the breeding season, when their calls take on distinctive sounds. This means one unusual organ contributes to climate tolerance and communication. Fossils show that similar animals endured conditions far harsher than those faced by many antelope today. Their survival reminds us that some of the strangest features in nature make perfect sense once the environment that shaped them is understood. Irish elk carried some of the largest antlers ever produced by any deer. Despite the name, this animal was neither restricted to Ireland nor closely equivalent to modern elk. Megaloceros giganteus was a giant deer whose antlers could span well over 3 meters from side to side. Growing them required an extraordinary annual investment. Like living deer, males shed and regrew their antlers, rebuilding these immense structures from bone each year. The energy and minerals needed for that process must have been substantial. Their huge size probably evolved through sexual competition. Males with impressive antlers may have gained advantages when displaying to rivals or attracting mates. Yet such extravagant structures also came with costs. Moving through dense woodland would have been difficult, which may help explain the animal's strong association with open habitats. The antlers have inspired speculation that they caused the species' extinction, but that simple idea is not well supported. Megaloceros survived with them for thousands of generations. Its disappearance was more likely connected to changing environments and shrinking suitable habitat. The antlers were not a fatal mistake. They were a spectacular adaptation that worked until the world around the animal changed. Despite their name, Irish elk lived far beyond Ireland across Eurasia. Their fossils have been discovered from Western Europe deep into Asia. Ireland became especially famous because its peat bogs and lake deposits preserved magnificent skeletons in large numbers. The abundance of discoveries there gave the animal its misleading common name. In life, however, Megaloceros occupied an immense range that included open woodlands and grasslands across much of temperate Eurasia. Populations responded to repeated climate shifts by expanding and contracting as suitable habitats moved. Some of the youngest known remains come from regions far to the east, showing that the species survived there after it had disappeared from much of Western Europe. This geographical history changes the way we picture it. The giant deer was not an isolated curiosity from one island. It was a widespread Pleistocene animal that experienced many different landscapes and climates. Ireland simply became one of the best places for humans to discover its remains. The name survived because history remembers fossils through the places where they are found, not always through the full territories the living animals once occupied. Ice Age moose expanded into new northern habitats as glacial environments changed. Moose are strongly associated with boreal forests today, but their deeper history reflects repeated movement as climate reorganized the north. During colder phases, glaciers erased habitat across huge regions. When ice retreated, new wetlands and young forests developed along the changing margins. Moose populations could expand into these freshly available landscapes. Fossils and genetic patterns reveal that northern mammals repeatedly shifted their ranges rather than simply remaining in one place throughout the Ice Age. Moose were particularly well suited to environments rich in woody browse and aquatic plants. Their long legs allowed them to move through deep snow and marshy ground, while their broad muzzles were adapted for feeding on branches and soft vegetation. Unlike many giant herbivores, the lineage survived the great Pleistocene extinctions and continued exploiting the new environments that appeared afterward. Their modern northern range is therefore the latest chapter of a much older pattern of movement. When glaciers vanished, moose did not merely endure the change. They followed the transformation and occupied habitats created by the retreating ice itself. Pronghorn relatives were once far more diverse across North America than they are today. The living pronghorn is the last survivor of a family that once included many different forms. During earlier parts of the Pleistocene and before it, North America supported several pronghorn relatives with horns arranged in shapes unlike anything alive now. Some carried multiple prongs or complex branching structures. Others differed greatly in body size. This diversity flourished because the family had evolved entirely in North America and occupied a range of open country niches. By the end of the Ice Age, most branches had disappeared. Only the lineage leading to the modern pronghorn survived. Its exceptional speed has sometimes been explained as an adaptation to outrunning extinct American predators, although exactly which predator drove that evolution remains debated. What is clear is that the animal now seems much more isolated than it once was. A single living species can hide the history of an entire family. The pronghorn running across modern Western plains is not an evolutionary oddity without context. It is the final representative of a much richer North American radiation. Harrington's mountain goat survived in places far south of modern mountain goat country. This extinct species lived across parts of the southwestern United States during the late Pleistocene. Fossils have been recovered from caves and dry deposits in places such as Nevada and the Grand Canyon region. Its presence there reflects a cooler world in which habitats resembling modern mountain environments extended much farther south. Harrington's mountain goat was smaller and more lightly built than the living mountain goat. It occupied rocky terrain where steep slopes could provide protection from predators. Preserved dung and bones from caves have helped researchers reconstruct its ecology with unusual detail. As the climate warmed, vegetation zones shifted upward and northward. Suitable habitat became increasingly fragmented. Eventually, the species disappeared while its northern relative survived. The story is a clear example of how warming can trap cold-adapted animals on shrinking islands of habitat. A desert canyon that now feels inhospitable to mountain goats could once support them because the surrounding climate was fundamentally different. Their fossils turn modern geography into evidence of a lost climatic world. Peccaries wandered through Ice Age North America in species that no longer exist. Several kinds of peccaries lived across the continent during the Pleistocene. One of the best known was the flat-headed peccary, which had a broad skull and long limbs. Another was the long-nosed peccary, whose elongated snout gave it a distinctive appearance. These animals ranged much farther north than living peccaries generally do today. Fossils have been found in regions that now experience cold winters, showing that extinct species tolerated climates, unlike those favored by many modern relatives. It traveled in groups and fed on varied plant material. Their remains appear in caves and other fossil deposits alongside animals that have also vanished. When the Pleistocene ended, the North American peccary community was dramatically reduced. Only a small number of species survived farther south. This disappearance is easy to overlook because peccaries still exist. Yet the family lost much of its diversity and range. The modern animals are survivors from a lineage that once occupied a far larger ecological stage. Ice Age North America contained several different answers to the question of what a peccary could be. Giant beavers reached roughly bear-like proportions compared with their modern relatives. Castoroids was one of the largest rodents ever to inhabit North America. Adults could reach more than 2 meters in length and weigh as much as a large person, with some estimates climbing well above that. Its skull was massive, and its front teeth were proportionally huge. Yet its body was not simply that of a modern beaver scaled upward. The tail was likely narrower, and the anatomy of its limbs suggests a different style of swimming. Giant beavers lived near lakes, ponds, and wetlands across much of the continent. Fossils are particularly common in areas shaped by glacial waterways. Their size must have made them conspicuous members of those communities. A modern beaver can transform a landscape, so it is tempting to imagine an even larger relative doing the same. The evidence, however, points toward a very different ecological role. Castoroids appears to have depended heavily on aquatic vegetation rather than engineering rivers through tree cutting. Its enormous size therefore belonged to a lifestyle but has no exact surviving equivalent. Unlike modern beavers, giant beavers had teeth suited to a very different lifestyle. The incisors of castoroids carried pronounced grooves running along their front surfaces. Their shape differed from the broad cutting teeth modern beavers used to fell trees. Microscopic wear and chemical evidence suggest that giant beavers fed largely on aquatic plants. Their teeth may have been useful for slicing tough reeds and other wetland vegetation rather than gnawing through trunks. No convincing evidence shows that they built dams in the manner of living beavers. Their ecology therefore depended on wetlands that already existed rather than on creating extensive ponds themselves. This distinction matters because body resemblance can be misleading. Custoroids belonged to the beaver family, but it had taken that heritage in a separate direction. The modern beaver became an ecosystem engineer with powerful wood-cutting teeth. Its giant cousin evolved into an enormous wetland herbivore with a specialized feeding system. When Ice Age lakes and marshes changed after glacial retreat, that dependence may have become a serious disadvantage. A familiar family had produced a giant whose life worked according to a completely different set of rules. Australia once supported giant wombat relatives weighing several thousand kilograms. The largest belonged to a group of marsupials called diprotodontids. Their bodies were heavy and barrel-shaped, supported by thick limbs adapted to carrying enormous mass. These animals were related to wombats and koalas, yet some reached dimensions closer to a rhinoceros. Their front teeth formed large cutting incisors that could crop vegetation efficiently. Fossils occur across much of Australia, showing that giant herbivorous marsupials succeeded in many different environments before their extinction. They lived in a continent with no native hoofed mammals like cattle or deer. Marsupials had instead evolved to occupy many of the large herbivore roles filled elsewhere by placental mammals. This produced familiar ecological functions inside completely unfamiliar bodies. To an observer arriving from another continent, the landscape would have seemed both recognizable and strange. Large plant eaters still moved across open country, but their evolutionary ancestry was uniquely Australian. When these giants disappeared, no living marsupial remained at anything close to their scale. The continent lost an entire category of huge mammalian herbivore that had existed there for millions of years. Diprotodon was the largest marsupial known to have walked the earth. A full-grown individual could stand roughly as high as a tall person's shoulder and weigh several tons. Its skull was enormous, with large forward-projecting incisors that gave the face a distinctive profile. Despite its intimidating dimensions, Diprotodon was a herbivore. It probably browsed on shrubs and other vegetation across a wide range of Australian environments. Fossil deposits sometimes contain many individuals together, suggesting that at least some populations may have gathered socially or concentrated around important resources. One famous site contains large numbers of Diprotodon remains associated with what was once a water source. During severe drought, such places could become both essential and deadly. The species survived until late in the Pleistocene, which means the first humans in Australia encountered it. Aboriginal oral traditions have sometimes been compared with memories of giant extinct animals, although direct connections are difficult to demonstrate scientifically. What fossils establish beyond doubt is remarkable enough. Australia once had a marsupial built on a scale usually associated with rhinoceroses and elephants, yet its closest living relatives are far smaller. Giant kangaroos included powerful species that may have browsed rather than grazed. Not every prehistoric kangaroo moved or fed like the familiar red kangaroo. Members of the extinct group Astenorinae developed deep skulls, powerful jaws, and teeth suited to processing leaves. Some stood exceptionally tall and carried heavily muscled bodies. Their anatomy suggests that at least certain species relied strongly on browsing vegetation rather than grazing open grasslands. That dietary difference would have shaped where they traveled and how they responded to environmental change. Their locomotion may also have been unusual. Some researchers argue that the largest short-faced kangaroos were poorly suited to rapid hopping and may instead have walked upright using alternating steps. This interpretation remains debated, but the skeleton clearly differs from that of modern high-speed kangaroos. Australia had therefore produced giant marsupial herbivores that challenged nearly every modern expectation of what a kangaroo should look like. They were not oversized versions of animals bounding across present-day plains. They belonged to extinct branches that experimented with new diets proportions, and perhaps even entirely different ways of moving. Some extinct kangaroos had faces dramatically shorter than those of living kangaroos. Procoptodon and its relatives developed skulls that looked almost compressed from front to back. The muzzle was reduced while the jaw became deep and powerful. This architecture brought the chewing muscles closer to the teeth, allowing strong forces during feeding. The front teeth could grasp leaves and twigs, while the rear teeth processed tough plant material. Procoptodon goliath was the largest known species and stood taller than most humans when upright. Its feet were equally unusual. Instead of spreading weight across several toes like many modern kangaroos, each foot was dominated by one enormous central toe. That gave the limb an almost hoof-like appearance. The combination of a short face and specialized feet makes the animal seem less like a familiar kangaroo the longer its skeleton is examined. Evolution had taken the basic marsupial body into a direction that vanished completely after the Pleistocene. Modern kangaroos preserve only part of the family's former diversity. Their extinct relatives once explored forms so unusual that even recognizing them as kangaroos can require a second look. Paleontology was a marsupial predator armed with extraordinary slicing cheek teeth. Its common name is the marsupial lion, but Thylacoleo was not closely related to true cats. It descended from herbivorous marsupial ancestry and transformed parts of that inherited dental system into formidable weapons. The third premolars became enormous blade-like teeth that met like shears when the jaws closed. They could slice through flesh with remarkable efficiency. The front incisors were also enlarged and may have helped grip prey. Strong forelimbs ended in a partly opposable thumb carrying a large claw. This gave the animal powerful control at close range. Bite force studies suggest that Thylacoleo generated exceptional force for a mammal of its size. Its feet retained climbing adaptations, raising the possibility that it could scramble onto trees or rocky surfaces despite being a substantial predator. Fossils occur across Australia, showing that it occupied a broad range. Nothing quite like it survives today. The continent had produced a carnivore by modifying a marsupial body plan in a direction that converged on the ecological role of a big cat without ever becoming one. Australia's giant monitor lizard Megalania shared its world with enormous marsupial mammals. Varanus priscus belonged to the same family as living monitor lizards and Komodo dragons, but it reached far greater size. Estimates vary because complete skeletons are rare. Even conservative reconstructions place large individuals among the biggest terrestrial lizards known. It lived during the Pleistocene and overlapped with giant kangaroos, Diprotodon, and other Australian megafauna. As a close relative of modern monitors, it probably possessed sharp, recurved teeth suited to cutting flesh. Whether it used venom in the same biological sense as some living monitor lizards remains uncertain, but its bite alone would have been formidable. The presence of such a reptile complicates the usual mammal-centered picture of Ice Age predators. Australia supported a large carnivore whose ancestry stretched back through reptiles rather than marsupials. Humans may have encountered Megalania after arriving on the continent, although the precise timing of its final disappearance remains debated. An Australian Pleistocene waterhole could therefore attract enormous marsupial herbivores, while one of the largest land lizards ever known moved through the same landscape. Genyornis was a huge flightless bird that lived alongside Australia's first people. Standing around 2 meters tall, Genyornis belonged to a uniquely Australian group of large flightless birds called dromornithids. Its heavy body and powerful legs made it a striking presence, although it was probably a herbivore rather than a giant predator. The species survived until relatively late in the Pleistocene, creating a period of overlap with humans after they reached Australia. Burned eggshell fragments found at archaeological sites have been central to debates about whether people collected and cooked the eggs of large birds. Researchers have argued over which species produced particular shells, but the wider evidence confirms that humans entered a continent still inhabited by enormous birds. Geniones disappeared during a period of major ecological change that also affected many large marsupials. Climate stress and human activity have both been investigated as contributing factors. Its extinction removed the last member of a bird lineage that had existed in Australia for millions of years. Modern emus provide no exact substitute. Geniones belong to a separate evolutionary experiment in becoming large, terrestrial, and permanently grounded. New Zealand's giant moa survived the Ice Age before disappearing much later. Moa were not victims of the great extinction wave that ended the Pleistocene. They survived for thousands of years into the recent past because New Zealand remained isolated from human settlement far longer than most large landmasses. Several species evolved there, ranging from turkey-sized forms to giants that could stand more than 3 meters tall when stretching their necks. None had functional wings. In fact, moa had lost the external wind bones entirely. Their ecological roles varied between browsers and other plant-feeding specialists. The absence of native terrestrial mammalian herbivores allowed birds to dominate niches occupied by large mammals elsewhere. That world changed rapidly after Polynesian settlers reached New Zealand in the late 13th century. Intensive hunting and habitat alteration followed. Within only a few centuries, every moa species was extinct. Their survival beyond the Ice Age makes them useful for understanding how isolation can postpone extinction until a new pressure arrives. New Zealand carried part of its prehistoric giant fauna almost into the age of written history elsewhere. Madagascar's enormous elephant birds also outlived the end of the Pleistocene. These flightless birds survived on Madagascar until roughly the last 1,000 years, long after mammoths and many other famous Ice Age giants were gone. Some species were among the heaviest birds ever known. Their eggs were equally extraordinary and could hold the contents of well over 100 chicken eggs. Fragments still occur across parts of the island. Elephant birds belong to a branch of flightless birds whose closest living relatives turned out, surprisingly, to include the much smaller kiwi of New Zealand. Genetic research revealed this connection across an enormous oceanic distance. Their long survival reflects Madagascar's isolation and the late arrival of humans compared with most continents. Archaeological evidence indicates that people interacted with these giant birds, and hunting probably contributed to their eventual disappearance alongside habitat changes. They remind us that the age of giant animals did not end everywhere at the same moment. On isolated islands, some remarkable lineages persisted deep into the Holocene. Human communities could therefore encounter animals whose proportions belonged to a world that had already vanished elsewhere. South America hosted giant flightless birds long after their dinosaur ancestors vanished. The Phorus racids are often called terror birds because many were large predators with massive hooked beaks. Their lineage first evolved long before the Ice Age, but some survived into the Pleistocene. Certain species stood well over 2 meters tall and used powerful legs to move rapidly across the ground. Their skulls were enormous relative to the body. Biomechanical studies suggest the beak was particularly well suited to strong downward strikes rather than prolonged sideways struggles. These birds flourished when South America had few large placental mammalian carnivores. After the continents connected, they encountered newcomers from the north and eventually disappeared. One genus even expanded into North America before the lineage vanished completely. Their existence is a reminder that birds themselves are living dinosaurs. In South America, one branch evolved back into towering ground predators that occupied roles mammals filled elsewhere. The asteroid had ended the age of non-avian dinosaurs tens of millions of years earlier, yet their feathered descendants later produced formidable terrestrial hunters on a continent with its own unusual PEML. Evolutionary history. Ice Age footprints reveal mammoths walking across landscapes beside ancient human travelers. At places such as White Sands in New Mexico, fossilized footprints preserve movement in a way bones never can. Mammoth tracks cross ancient surfaces that also contain human footprints from the late Pleistocene. The tracks do not merely prove that both species lived in the same region. They show individuals physically moving across the same ground within landscapes shared at human scale. A footprint can preserve direction, speed, and even changes in behavior. The depth of an impression can hint at body weight or the softness of the mud beneath the foot. Sequences reveal whether an animal walked steadily or altered course. Human tracks sometimes follow pathways used by large mammals, raising fascinating questions about observation and pursuit. Unlike a butchered bone, a trackway captures life before death entered the story. One moment, an enormous animal stepped into damp sediment. Later, the surface hardened and was buried. Thousands of years afterward, erosion revealed the journey again. For a brief stretch of ground, an Ice Age landscape became readable, almost like a sequence of actions. Some fossil trackways captured giant ground sloths apparently reacting to approaching humans. White Sands preserves an especially intriguing set of tracks where human footprints occur within and around the much larger impressions of giant sloths. In several places, sloth pathways appear to change when human tracks approach. Some impressions form unusual circular or twisting patterns rather than continuing straight ahead. Researchers have proposed that these could record defensive movements by animals confronting potential hunters. Human footprints sometimes step directly inside sloth tracks, which may indicate people following the animals closely. The interpretation is debated because tracks record movement without explaining motivation. Still, the spatial relationship is difficult to dismiss. This is not simply evidence that both species occupied the same region centuries apart. The track surfaces can preserve interactions on a much shorter timescale. If the defensive interpretation is correct, they record a tense encounter without a single bone or weapon surviving. A person approached. A giant sloth altered its movement. The ground captured both responses. Few archaeological sites bring us closer to the physical choreography of humans meeting extinct megafauna in real time. Frozen soil can preserve ancient animal DNA, even when no bones remain nearby. Genetic material does not always need to come from a tooth or skeleton. Animals constantly shed microscopic biological traces through hair, skin cells, urine, and feces. In cold environments, fragments of that DNA can become trapped in sediment and remain detectable for extraordinary periods. Researchers can collect cores from ancient frozen ground and identify species that once lived there without finding a single visible body part. This method is called environmental DNA analysis. It has transformed the study of Ice Age ecosystems because conventional fossils are unevenly preserved. A species might have occupied a region, yet leave few bones behind. Sedimentary DNA can reveal its presence anyway. The technique can also detect plants and microorganisms from the same layer, allowing scientists to reconstruct entire communities. Contamination must be controlled carefully because modern DNA could easily distort the results. When done properly, frozen mud becomes a biological archive. A handful of sediment can contain evidence from animals that walked across the landscape tens of thousands of years ago and left nothing more obvious behind. Cave paintings preserve details of Ice Age animals that fossils alone cannot reveal. Bone can reconstruct a skeleton, but it cannot tell us everything about the living surface of an animal. Paleolithic artists sometimes filled that gap. Their images show main shapes, coat patterns, body proportions, and behaviors that would otherwise be lost. Mammoths were drawn with high shoulder profiles and curved backs. Horses sometimes appear with distinct markings. Lions were depicted with external features that skeletons could never preserve. The accuracy of many images suggests close observation rather than imaginative invention. Artists knew how these animals carried their heads and how their bodies looked in motion. Some species appear repeatedly across widely separated sites, which allows comparisons between artistic traditions and zoological evidence. Not every image should be treated as a photographic record, because prehistoric art also had cultural meaning. Yet the biological details can be remarkably informative. These paintings give extinct animals something fossils cannot provide on their own. They restore the visible body. For scientists studying the Ice Age, ancient human observers sometimes function as unexpected witnesses who left field notes in pigment and charcoal. Ancient DNA has completely rewritten the family trees of several famous Ice Age predators. Appearance can be deceptive when evolution produces similar bodies in different lineages. Genetic material recovered from old bones has exposed relationships that anatomy alone could not resolve. Some extinct carnivores, once assumed to be close relatives of living species, have turned out to represent much deeper branches. Others show unexpected mixing between populations that fossils had been assigned to separate categories. DNA can also estimate when lineages split and reveal migrations invisible in skeletal shape. This has transformed paleontology from a science based largely on bones into one that can reconstruct heredity directly. The process is difficult because DNA fragments break into smaller pieces after death and can be contaminated easily. Cold environments offer the best preservation, which is why many breakthroughs come from northern fossils. Each successful genome adds another layer to the evolutionary picture. The Ice Age bestiary has not changed physically, but our understanding of who was related to whom has shifted dramatically. Familiar names can hide family histories far stranger than their outward resemblance ever suggested. Isotopes preserved inside fossil teeth can reveal where individual animals once migrated. As a tooth grows, minerals from food and water become locked into its enamel. Different regions carry distinctive chemical signatures because local rocks, rainfall, and soils vary. Animals absorb those signatures as they eat and drink. Scientists can compare isotope ratios along a tooth with geological maps to estimate where the animal spent different parts of its life. Because enamel does not remodel after forming, the chemical sequence remains preserved. This technique turns a tooth into a geographical record. Researchers have used it to trace movements of mammoths and other large herbivores across enormous territories. Some individuals followed regular seasonal routes. Others changed their ranges as they matured. The method can even reveal whether an animal found at one site had grown up somewhere entirely different. Fossils therefore hold evidence not only of species distribution but of individual journeys. A single tooth may record years of movement through landscapes that have since changed beyond recognition. Migration paths once known only to the animal itself can be reconstructed thousands of years after the final step. Tooth wear can reconstruct the seasonal diets of animals dead for millennia. Every meal leaves microscopic evidence. Hard particles scratch enamel, while different foods create distinctive patterns of pits and abrasions on chewing surfaces. By examining these marks under magnification, researchers can infer whether an animal recently ate tough grass, softer leaves, or other vegetation. The method is especially valuable because it can capture diet over relatively short periods before death. Another approach examines the larger shape of worn tooth surfaces. which reflects feeding patterns accumulated across longer spans. Together, these techniques allow scientists to separate animals that might otherwise look similar from their skeletons alone. They can reveal seasonal changes and show whether populations adjusted their diets when preferred foods became scarce. This helps researchers understand how flexible a species was when climate shifted. Two herbivores living in the same landscape may have been using completely different parts of the vegetation. Teeth preserve that ecological separation. Long after the stomach and plants have vanished, the damage left by chewing remains. An extinct animal's final months can still be written into the microscopic scars on its enamel. Many Ice Age survivors are still living quietly among us today. The end of the Pleistocene did not erase its entire animal world. Reindeer still cross northern landscapes. The Skoxen continue to withstand Arctic winters. Wolves remain major predators across parts of the northern hemisphere. Brown bears, moose, Arctic foxes, and saiga also carry lineages that experienced glacial climates firsthand. Even species that seem ordinary today can have histories extending through landscapes crowded with giants. Their survival provides scientists with living models for understanding extinct neighbors. Behavior, physiology, and social structure can offer clues when interpreted carefully. Yet these survivors should not be treated as unchanged relics. Their populations evolved after the Ice Age and adapted to new environments. Some shifted range dramatically. Others passed through severe population bottlenecks. What survives is continuity rather than perfect preservation. The remarkable point is that the modern world still contains animals whose ancestors watched glaciers advance and retreat. Walking past one of these species means seeing a lineage that successfully crossed one of the most turbulent environmental transitions in recent Earth history. Climate change transformed the habitats of different Ice Age species in dramatically different ways. Warming after the last glacial maximum did not simply make every region warmer by the same amount. Rainfall patterns changed. Forests expanded into open country. Wetlands formed in some areas, while others became drier. Seasonal conditions shifted at different speeds across continents. This created winners and losers according to each species' ecological needs. An animal adapted to open steppe could lose feeding habitat as trees spread. A woodland browser might benefit temporarily from the same transformation. Species able to move quickly could follow suitable environments, while isolated populations could become trapped. The speed of change also mattered because vegetation sometimes reorganized faster than slow-breeding mammals could respond. Researchers reconstruct these shifts using pollen, ancient DNA, sediments, and fossils. The resulting picture is far more complicated than a single warming event. Ice Age ecosystems were dismantled region by region through different combinations of climate and geography. This helps explain why extinctions did not happen everywhere simultaneously. Each species faced its own version of the changing world, and survival depended on how well its particular adaptations matched what came next. The disappearance of giant herbivores reshaped ecosystems long after the animals themselves vanished. A mammoth or giant sloth influenced far more than the plants it ate. Large herbivores broke branches, trampled vegetation, transported nutrients, and moved seeds across long distances. Their bodies physically altered the structure of habitats. When those animals disappeared, every one of those processes changed. Some grasslands may have become easier for shrubs or trees to invade because fewer enormous grazers were suppressing them. Nutrients once carried across landscapes in dung became less mobile. Plants that depended heavily on megafauna for seed dispersal had to survive through different relationships. Predators and scavengers lost huge sources of food. Even fire patterns may have shifted as uneaten vegetation accumulated differently. Ecologists sometimes call these consequences ecological legacies because they can persist long after extinction. Modern landscapes are therefore not simply natural systems with a few missing species. Their structure has developed for thousands of years in the absence of animals that once exerted enormous influence. To imagine the Ice Age accurately, we must restore not only the giants themselves, but also the ecological work they performed every day. And so, our journey through the Ice Age begins to settle behind us. We have wandered through a world filled with animals that seem almost impossible now. Mammoths crossed frozen grasslands. Giant sloths moved through the Americas. Saber-toothed cats waited for the right moment to strike. Vast herds traveled across open country, while powerful predators followed close behind. We have seen how deeply these animals were shaped by their world. Some carried thick coats against the cold. Others evolved extraordinary teeth, armor, claws, or antlers. Many traveled across continents as the climate changed around them. And we have also seen how much evidence they left behind. Bones can tell us how they moved. Teeth can reveal where they traveled. Frozen ground can still hold fragments of their DNA. Ancient footprints can preserve a single journey across soft earth, long after the animal itself has vanished. For a moment, you can imagine that old landscape growing still again. The wind moves across the grass. A distant herd passes slowly through the open country. Somewhere beyond them, the ground is marked with tracks that will remain hidden for thousands of years. But there is nothing more you need to follow now. Let those distant animals drift away. Let the details soften. Allow your breathing to slow naturally, and feel the weight of the day begin to leave you. If you enjoyed this journey, you are always welcome to like, subscribe, or leave a thought below. And if you happen to still be awake, there is another sleepy science journey waiting for you on the screen. You can follow it if you would like, or simply let the sound fade into the background as you rest. For now, let your eyes grow heavy and allow the ancient world to disappear once more into the night. Sleep well, and good night.